My name is Marcelo Bursztein. I'm founder and CEO of Novacine AI, and I left my email address. So please feel free to reach out to me in the next few weeks if you find this talk interesting and you want to continue the conversation. I'll be happy to receive an email from you and chat more. Well, let me get this out of the way. I'm not a technical person. Some people say I'm dangerous enough. No, I know enough to be dangerous. There you go. That's how it goes. But the reality is that I've been building digital products for over 20 years now, primarily for public sector clients. And my background is been in UX design. So as a person in UX design, I've always been pulled into the intersection between business and technical teams. Business will bring their business requirements, and we will have to translate them into functional requirements so that the technical team can build products that the business can use and, most importantly, sell to customers. And a little bit about Novacine AI. We build a SaaS platform that enables business users to bring in their data and to apply AI to that data without writing code. If only were that easy. In the last couple of years, through the building of the platform, we realized that what initially started as a vision to abstract complex technology behind elegant interfaces, the reality is that AI is really difficult, and you really have to work at the problem to get it right. So what happened is that our tool turned into a platform for collaboration between business users and data scientists. And that's where we are today with our tool. About the talk, this is going to be about a 20-minute presentation with 10 minutes Q&A. And just about that Q&A, I mean, please ask questions. Yes, I will take questions. But also, if this talk sparks any thoughts and ideas that you want to share here, please share them. I'm here to share my experience here with you, but I'm also here to learn from all of you and everybody on Zoom as well, please. I'm going to present two case studies that demonstrate this type of cross-discipline collaboration from teams coming from very different backgrounds. And I'm going to also explain the benefits that that collaboration created for both teams on both sides of the domain expertise divide. So no-code tools. Raise your hand if you used or are used in the past no-code tools to do your job. Oh, 1, 2, 3. How do you feel about it? You can give me some body language.
I used it for planning, and I used the no-code part of the NLP, and then after I realized it switched for me, and I ended up using it for.
Okay.
So you summarize, step a little closer.
Okay, great.
Summarize.
Okay, perfect. So I hear that you started using no code, and then you moved to using the backend. Is that?
I use the API for entity recognition and analysis. So I realized that it's good for me. I started using the local version. And then I realized it's good for me. I moved to the actual code because I wanted to run it in a scale. So I didn't run it in a scale. So.
There you go. Gotcha. Okay. And you, what was your opinion? Yeah or nay?
So exact functionalities, like there is upsides and downsides to it.
Okay, great. So what I'm hearing is that I started with no code. It got me somewhere there, but then I really had to bring it back to the real thing to do the rest of it. Something like that, right? It's good for a start, but not for the whole way. And you know, I felt the same way throughout my career. I always felt like no-code tools were limiting. They were limiting me and my creativity and my ability to solve problems. And you know, I have an anecdote that goes back 15 years ago. I was running a creative department at the time, and we had visual designers, and this was a very particular team in that they were very technical. You know, they were not just graphic designers, but they also wrote code, and they checked in code into repositories, ran version control on them. So it was a fantastic team, and we brought a tool called Dreamweaver. And I'm not sure if you guys here are old enough to know what that is, but Dreamweaver was, was made by Micromedia a long time ago, and then Adobe buys it in mid-2000s. And the promise of this tool was, this tool allows designers to create websites by just dragging and dropping elements into a canvas, and then magically the tool creates the code. And I remember we brought that in, and as soon as the designers will switch to the code view, they did not like what they saw. They saw dirty code, bloated code, and they did not want to check that into the repositories. They said, you know what, not good. And those who continue using it, they were using it as a glorified text editor. So no, it did not work. But here's the catch. I think the technology evolved a lot. And I'll tell you what, I was using myself a tool called Proto.io a couple of years ago to do version 1.0 of the NovaScene app as a prototype that I can show to my developers so they can build it for me. And that was not a no code, it was more a low code, because I could program some logic to create some interactions and behaviors. And I was really impressed. And I'm a guy, I like the code. I like to get my hands dirty, but I was quite impressed with how far it got me before we went to engineering. So before I talk about the case studies, I just want to mention two concepts that underpin my presentation here. The first one is interdisciplinary collaboration, and the second one is managing complex projects, and how both really will support the presentation. I gotta take you back to the 1980s, and that's me wearing a handsome red jacket on that rather cool vehicle. My dad is next to me. This must be, judging by my size and age there, looks like it's the late 70s. And one day I was with my uncle and he was fixing an engine. I think it was a small RV that he had. And he said to me, the reason why I can fix this even though I'm not a mechanic is because I know a little bit about a lot of things, okay? And he was fixing it, and then he said something that stayed with me. This is 40 years later. It totally stayed with me. He said, you know what, Marcelo, in the future, you're gonna have people that are going to specialize, not in this side of the engine, but the component inside of this component of the engine. And they won't be able to work across the stack, across the engine in the white space. And that stayed with me. And you know what? I think he was right. I think he was right. I think the world today, we have specialists, and I'm sure that many of you here and many of you on Zoom are very specialized and very laser focused and deep knowledge about specific things. And if you add to that the fact that technology is everywhere and it enters every domain, especially software, you end up with a situation where you inevitably will have to collaborate across disciplines, across expertise silos. And I love this excerpt from a paper called Jack of All Trades and Master of Knowledge, the role of generalists in novel knowledge integration. And the researchers say that when they wrote this paper, they were motivated by a paradox where impactful discoveries are the result of diverse knowledge input, yet achieving diversification is increasingly difficult as knowledge accumulation leads to division into narrower knowledge areas and increased specialization. I love how that captures the view around specialists and generalists. The second thing is complex project management. And for this one, I want to borrow from Andrew Ng in a recent issue of The Batch, his newsletter, where he goes, compared to traditional software that begins with a specification and ends with a deliverable to match, machine learning systems present a variety of unique challenges. And then he goes on to say, we don't know how accurate the system will be in advance. We might need a costly initial data collection phase. After getting the initial data set, we might come back and ask for more or better data. And we might ask for this over and over. So while a traditional IT software project looks like a linear three-step process where you plan, you build, you deliver, and you celebrate, Machine learning has a lot more caffeine in it. You plan, you build, you go back to the drawing board, you reformulate your hypotheses, you think of the problem from a different angle. And sometimes, worst cases, your POC never leaves the shelf or sees the light of day in production. Is there a better way? I think so. And for that, we need better collaboration. And that brings me to the two case studies I wanted to talk about. The first one is a project called the Journalism Representation Index. And in this case, the experts are journalists and professors from Toronto Metropolitan University. And just a quick brief about the project. The Journalism Representation Index, or JERI, offers news outlets and media watchdogs a rare view of how journalists fare in representing all of the key stakeholders in stories of heightened public interest. That's the URL for the project if you want to check it out, really interesting. They came to us and they said, we want to know how representative a news article is based on who is quoted as a source. Now, what does that mean? Let me parse that out. So representative in this case means that, let's say, for instance, you have an article and the only source quoted in the article is the Toronto Chief of Police, then that article might be one-sided. And the framing of the news piece might have an authority sort of perspective, right? Whereas if you have another news article and you have the Toronto Chief of Police, but you also have an expert from academia, and you have a political figure, civil society, and a celebrity. Now all of a sudden you have a more representative news article. So they said to us, can you write some code, an algorithm that help us compute the representativeness of this article? And our data scientist said, okay, well, we think that this is a two-step pipeline. We're gonna approach it as a fine-tuned BERT, NER, and as a second step, we're gonna do a multi-class classification where we're gonna assign a class from the very different classes that we have, whether somebody's an authority, a political figure, a celebrity, and et cetera. So they built the pipeline and they deployed it onto the app, and the app allowed the journalists to upload new news articles and put them through the pipeline and see the results, see the predictions that the algorithm was outputting. They were able, the journalists, they were able to export that data, annotate, and provide corrections to that data, feed it back to the data science team, retrain the models. And it empowered the journalists and the research analysts, the research assistants at the university, to get involved with the quality assurance and the quality control of the product that we were building. And that helped, and most importantly, I think, in my view, is that it helped develop a more precise communication between the two teams that were coming from very different backgrounds, something that is really difficult in practicality to achieve. The outcome is that the initial assumption from the data science team was just too simple. The solution wasn't enough. The deeper understanding of article structure from a journalistic point of view gave the data scientists new nuance and understood the challenges that came with that nuance. And it allowed them to revisit the initial assumption. So what started as a two-step pipeline, it ended up being a four-step pipeline where we first extract person using an NER, then we have a source detection to determine whether that person is in fact a source in the article, because the article could be talking about somebody, but it's not quoted in the article. A source type classification, that was the second step on the old pipeline, and co-reference resolution, which is a really interesting problem, where in a news article, we have somebody who's introduced in the first paragraph, but is not quoted until later in the article. And then when they're quoted, there's no context as to who they are. So how do we solve that disconnected context problem? Or somebody might be introduced by name and last name and then refer to them as she or him or her or he. How do we count that? The second project was an analysis of open-ended survey responses, many different surveys. And in this case, the expert is a research analyst at a public engagement and opinion research unit at the Government of Canada. The unit, just briefly to give you context, engages Canadians and stakeholders on various issues by conducting public engagement activities, such as consultations, public opinion research, and by using external advisory bodies. Here's a URL if you want to check out more about that unit. They came to us and they said, we want to understand what people think about various subjects. Fairly blanket statement, right? If there's some. But anyway, so NLP engineers look at this and they say, well, we think it's text classification, clustering, topic modeling, sentiment analysis, that tool set, that type of tool set to that problem. So what they did is that they used the no-code platform to test a few unsupervised models against different data sets to understand the degree to which these models generalize well enough to provide background. Yes, Seth?
5 minutes.
Oh, I got to speed up. So at one point, the analyst said, well, I need a word cloud, but that really what they were asking was, we need a context-aware term frequency analysis tool so that we can actually make sense of the data. And this interaction created opportunities for R&D exploration to generalize models through context. The outcome is that it created a close working relationship between the analyst and the data science team. The data scientists got embedded into the analyst world, both created a better understanding of their way of thinking of each other's world and just better communication all around. The conclusion is that in both cases, and this is probably the most important bullet in my PowerPoint, if you ask me, is that initially domain experts expressed their need within the confines of what they understood to be possible. They came to you and they said, we want you to build this for me, whereas they should have come to you and say, we want to achieve this outcome or solve this problem, and let the collaboration dictate the how we're going to get there. So that's, that to me is like really the underscoring side of it. In both cases, better collaboration, better communication, and looking at the pain points as the experts were experiencing through the no-code tool gave the data science team incredible opportunities to see specifically what was frustrating them and where solutions were inadequate. Teams sharpened their communication and it broke down barriers between silos. I know it's cliche, but it's exciting when you see it in real life materialize in front of you. I'm going to skip bonus and I'm going to say the summary is that I used to think no-code tools were limiting. They made the practice simpler, which is not a good thing, but they create abstractions that can be helpful, put diverse teams in a level playing field, and allow data scientists to do more interesting work by leveraging things that are already done for them. So cheers to a world with less caffeine and more celebration. Thank you, everyone. And thank you, Seth. Thank you, Basis, for hosting. Thanks, everyone here, for coming out. It's been 2 years of being locked down, and thank you, everyone on Zoom.
Right. Do we have any questions for Marcelo from the live audience? I'm not seeing any online. Someone posted about the pronunciation of capture.
I must have done a good job then.
All right, thank you, Marcelo.
I'll ask one if there's no
Want to come up so you can be heard?
I guess I was just looking for a little bit more specific example of we all want that better collaboration. We all want that understanding, right?
Right.
We all want that magic wand, that person. But in practical terms, how are you bridging that gap? Can you give a more specific example of how are you actually doing that?
Sure. So I'll just give you the walkthrough. So picture this tool online, web browser. The analyst, so the data science team built this pipeline. They deploy it to this tool. Now it's available in a drop-down that the analyst can select from. And they can select a column in their data set and say, okay, run this data set through the pipeline. The tool runs the data set through the pipeline. It pushes the results to the front end The analysts can see the results. And if you do that over a Zoom session, you can hear reactions and they can tell you exactly why things are not happening for them. They can export that enriched data set and make annotations on that enriched data set. Does that help?
Yeah, that helps a lot. It gives me a
Okay.
sense of how you're actually doing it.
Super, great.
Let's take one question that came in online.
Sure.
So I will do this to read the question to you, and then you can take it over. So Adil asks, in the first example, when did you study the data feature engineering? You seem to have gone straight into model development, skipping a core aspect of the data science method. Even transfer learning requires a degree of initial feature engineering to explore and understand the data, to determine the right model approach to take. You could have used T5 with the balanced encoder decoder for NLU, natural language understanding and natural language generation, with an active learning for process for annotation. So any kind of feature engineering going on up front here?
Yeah, it's a good question. And I did sort of skip that side. So apologies for that. I focused on modeling. But you know, one of the things that we really try to focus on at our company is to build unsupervised models that can generalize across data sets and problems. So, you know, it's true. One of the examples that I've run out of time to tell you about is that when we created the word cloud for the analyst said, hey, but the word Canada is the biggest word on the word cloud. I already know this is about Canada. Why do I care to see it so big? So we thought about, okay, well, you know, maybe we should have some pre-processing with custom stop words to remove the words that are unhelpful to the analyst. And then immediately we thought, yeah, but we don't want to do that. We don't want to hard code these pre-processing tasks. We want to extract context from the data itself. So we're always pushing for extracting context and feeding that into the pre-processing by looking at the context in the data. That's really what we at least focus on. And I understand, you know, the limitations of trying to push things to be generic, but that's really our long-term strategy as a company.
Let's stop there. Thank you, Marcelo.
Thank you.
All right, thank you to everyone in the audience. We're going to switch to our second speaker now, who is Philip Blair from Basis Technology. And let's see, Philip, do you have the PowerPoint loaded here?
Yes,
I'm going to let you find that, all right? Yeah, he's got to pull it up. Okay, give us a second, everyone who's watching on Zoom, while we pull up Philip's presentation. We're going to need to go to the Zoom share. Yep, share that one. Okay, take it away.
Okay, hi everyone. My name is Philip. I'm a research engineer here at Basis. This is our office, as you've heard. Yeah, so today I'm going to be talking about a research project that our team has been working on for, better part of a year now. And so let's jump right into it. So, yeah. So first I'm going to give just an outline of what this talk is going to look like. We're going to give a little deep dive into what entity linking actually is and what entity disambiguation is. Go into some background on pattern exploitation as a technique, and then look at how that technique can be applied to entity disambiguation and why we might want to do that. Then we'll take a look at some quick results and have a brief Q&A at the end. So, what is entity linking? This is a task in NLP where we're going to take a document, such as this sentence, Cambridge is a city in Massachusetts, and we want to identify pieces of that text which are mentions of entities in some knowledge base. Now, a knowledge base could really be any sort of database, but a good illustrative example would be something like Wikidata, which is the knowledge base that backs everything on Wikipedia. But these systems are designed to do two things. One, is detect the mentions of these entities in text. So finding the word Cambridge and finding the word Massachusetts. And this is a task known as candidate generation, which is roughly analogous to named entity recognition for those of you familiar with that. And then you have a disambiguation step, where once you've identified these candidates in your document, you need to determine which entity in each of your lists of candidates is the correct one for that given mention, if any. Sometimes you might want to say, you know, it's none of these. And so in this talk, we're going to be focusing on the second part of this process, disambiguation. And this is a tricky problem because in order for a system to do this automatically, it has to do a number of things. It has to look at the context in which the mention appears in a document. It needs to look at relevant fields on the knowledge base entity that you're considering linking to that mention. And it needs to kind of arbitrate between those two things in order to make an informed, coherent decision. So in this case, the system might say, okay, well, this Boston thing appears to be a city and it has something about Massachusetts in it. Then it might go look at the knowledge base and say, well, you know, I see that, you know, Q100 is an instance of city and it has a link to this other entity called Massachusetts. So maybe we give that a boost in our result list. However, you can think about if you were to write a hard-coded rule set for doing this, it would probably be very difficult to capture all nuance that's possible. And so we rely on statistics and machine learning in order to accomplish this, which is all fine and dandy, except in the real world, we have a problem with domain transfer. Especially with named entity linking, the bulk of data that we have to train these machine learning systems is based on generic news type data. And at runtime, when we're trying to run these systems on documents in the real world, that data often doesn't look like a Reuters article. For example, it might be talking about COVID cases, and maybe the statistics required to disambiguate in that context are a bit different than that required for Reuters. So now, being good data scientists, your first instinct might be, okay, great, we'll just go get data for all the domains that we're interested in, and then we'll train the model for that. However, the problem that we run into is the amount of data that's required to do this. So here I have a breakdown of the size of what's called the Ida-Connell data set. So for those of you who have worked in named entity recognition, you might know the Connell 2003 data set. It's kind of the gold standard for this task, or for that task, I should say. And Ida-Connell 03 is just that data set with linking information. And you can see that the training split of that data set has 18,000 mentions in it. And so because that's the amount of data required to get a working named entity linking system, we would, in theory, need to collect a similar amount of data for a different domain if we were interested in that. And we're talking about, you know, could be upwards of tens of thousands of dollars if you're working in a highly specialized domain to get this quantity of data. So that's kind of a non-starter. What we would like is a way to get these named entity linking systems up and running without that quantity of data. And so from here, we're going to pivot into some background of a technique called pattern exploitation training. And so this is a relatively recent technique from the past couple of years, where we try to leverage language models to be used in downstream tasks. If we think about what a language model is trained to do, usually, whether in a language model being something like BERT, T5, etc., they're typically trained on a task, on some form of a task known as masked language modeling, where the idea is you take a document, you pick some tokens, and you replace them with this special mask token. And then the goal of the system is to take that input sentence and predict which token, word the mask token originally was. Excuse me. So, for example, in this input, a properly trained system would tell us that dog is more likely to be this word than something like computer or squirrel. Now, this is a little toy example, but we can take that toy example and we can start playing with this idea, right? Because typically what you would do in the past is you would take these language models, throw a little classifier head on top of it, fine tune it on some examples, and then you have a classifier for your task. But maybe we don't need to do all that work. Maybe we can just start looking at what the language model understands on its own. So we looked at this first example. You know, I walked my pet blank yesterday. Okay, dog's more likely than cell phone, not too interesting. But, you know, what if we give it the sentence, you know, we are in blank Massachusetts, and the system tells us that Boston is more likely than Utah. You can start thinking, well, okay, maybe this language model has been exposed to enough text that it understands that Boston and Massachusetts have some sort of relationship to one another. Or, for example, you give it a sentence like Google is a blank based in the United States, and it says company is more likely than person. And so the language model can understand, okay, well, the sentence Google is a company based in the United States makes more sense than Google is a person based in the United States. And so from here, you can start thinking how maybe we can start leveraging this directly for specific tasks. And this is where pattern exploitation training comes in. And this task specifically, the system that we use specifically is a technique known as ADAPED. And the paper that it's from is down there in the bottom right. So imagine, for example, our goal is to take something like a product review from maybe like a product on Amazon or something and decide if it's positive or negative. Simple binary classification. So you can imagine that if we had a language model that's been exposed to a whole bunch of English text, and we give it the sentence, this is a positive review, this product sucks, and the sentence, this is a negative review, this product sucks, then the language model should give us a higher perplexity for the first example. Or in other words, the first example should be more surprising and less in line with what the language model would expect normal English to look like. Okay, now if you look at these two sentences, you see that they only differ by one word. So instead what we can do is we can just mask out that word and run our standard masked language modeling task on that input. And then we can just directly ask that pre-trained model, what's more likely, the word positive or negative? And suddenly, we now have a binary classifier from this pre-trained language model without using any training data. Now, of course, in reality, using this in a zero-shot fashion like this usually doesn't give the best results. So we do take some data and we fine-tune this process a little bit, but because of the quantity of data that these language models have been trained on, typically you don't need a whole lot of data. And so you're able to effectively do few-shot learning in this setup. And the intuition here is that because the language model has seen so much English and it knows what types of things make sense and what types of things don't, you don't need to reteach it everything from the ground up in order to get a model that's able to do a specific task. So, with this idea, we can ask, how can we do entity disambiguation? All we have to do is we have to find an appropriate sentence to feed into our model in order to use as our pattern. So in this example, we have Boston as a city in Massachusetts, a sentence we're well acquainted with at this point. And we produce two inputs that we're going to pass into this model. First, we have a little blurb that has the mentioned context, so this sentence up at the top. Then we have a description of the candidate that we want to consider for this mentioned candidate pair. In this case, you see a machine-generated description based off of fields on entity Q100's Wikidata information. And then at the end, we have this little question of is mentioned, so the token up at the top, which replaced the location of the mention in the input text. Is that Boston? Yes, and then we have a mask token, which is going to be either yes or no. And so we feed those two sentences, one for Boston Celtics, one for Boston, Massachusetts, into our language model, and we can look at which is more likely to have a yes token. And we can say, okay, that's more likely to link in this case. And so we can tune this with a few examples. And we have a disambiguation classifier. Now, in order to assess, in order to properly compare this to state-of-the-art systems, we have to plug it into a larger system. And the reason for that is most named entity disambiguation systems don't rely on just local context, like what you would find in that input that we just produced, but they also have a little bit of higher level reasoning. So for example, it might look at the sentence and say, okay, well, I kind of think this one's Boston, Massachusetts, and I kind of think this one is Massachusetts, the state. And because I think that about both of them, then I'm going to rank both of those higher, right? It's going to kind of look for a coherent set of entities to link in that document. And so in order to properly profile this, we took a state-of-the-art system called DCA. Now, understanding the system is not particularly important for this talk, but I'll give a very brief outline. Basically, what this system does is it's a simple linear neural network, which receives some handcrafted features, some of which are statistics based off of corpus frequency, some of which are things like the probability that the string Boston links to Boston, Massachusetts, like the entity on Wikipedia, and so on. These handcrafted features, and it produces a scoring algorithm out of it. Oh, and in addition, it also receives a contextual signal where as it scans through the document, once it links Boston, when it gets to Massachusetts, it knows that it already linked Boston. And so what we did is we just added a new feature to this neural network, which corresponded to the probability of a yes from our ADAPET tuned model. So when running this on the IDA dataset, which again is kind of the gold standard for named entity disambiguation, we find that the baseline results are more or less the same, which is okay for what we're trying to do because we're focused on transfer learning. And so these graphs show a few different things. On the y-axis, we have the accuracy on the data set, and on the x-axis, we have the amount of data which was used in order to train it. And the reason why this is interesting for what we're focused on is because it gives us a picture of how much training data is required to get the final accuracy of the model. So in other words, the further to the right, the elbow, so to speak, of this curve is, or sorry, further to the left it is, excuse me, the less data is required to train it. And there's four different lines, as you can see. We have a blue dotted line, which represents our baseline system, just the state-of-the-art DCA without anything we did. We have an orange line, which represents the DCA system plus what we did. Then at the bottom, we have just the ADAPET tuned system. And then above that, we have the DCA system, but only with its local features turned on, which is more directly comparable to that bottom line. Now, again, we find that the top two lines pretty much trail one another. And we do see a big gap between the bottom two lines. However, what's important to note is that the elbow of the bottommost line is much further to the left than the other lines, which indicates that the ADAPET component of our model is able to, I guess, saturate its accuracy with much less data than the others. And the reason why the other lines are all much higher is in part because the features that DCA uses are much more directly suited to this task. And I should also note that while you can collect a lot of these features for the IDA Connell data set, you can't necessarily collect them for any data set. Whereas with our ADAPET model, that would work with many more domains. And yeah, again, so looking at transfer to domains which are relatively similar to the training domain, we see that the performance of our model, which is the bottom row, more or less tracks the performance of the state-of-the-art, which is the top three rows here. And in fact, we do get state-of-the-art performance on one data set, but it really is pretty close. Now, let's start thinking about transferring to a more distinct domain that's not just other news data or other general news data. To that end, we created a data set focused on mental health news, which we called NEDMED, where we took 110 documents on mental health news and we annotated them for the same types of general entities like person, location, organization, etc. But in addition to that, we added specific medical entity types like disease, treatment, symptom, substance, etc. And on the right, we have a little snippet of what types of documents we have in that data set. And we can see that this data set is significantly smaller than the ida-conal data set by a magnitude of a lot. Anyway, so first of all, we see that our system is able to generalize to this domain much better than the other system, than the baseline system, pretty much across the board. In fact, by using very little training, by using almost no training data, our system is already about 10% better than the baseline system when it uses all of the training data. And I should note, what this graph is showing here is when you take a model that was trained already on the IDA data set and then further fine-tuned on successively larger portions of our NEDMED training data set. But again, so the zero-shot transfer, so you can see the bottom, the third row performance is better than the performance of the baseline system when it's trained on the NEDMED data set. Of course, when we train our system on the NEDMED data set as well, then the performance gets even better. But what this indicates is that this system is able to more readily adapt to a more diverse set of domains without degrading the performance on the baseline general news domain. So what's next with this approach? We could try it for more languages. The data that we've looked at so far is English only, and at basis, we like to focus on a large number of languages. We could look at more domains. We have looked at this mental health, medical news domain, but of course, there's a large variety of other domains out there we could consider. In addition, the Wikidata knowledge base is particularly well suited to a task like this because it's very rich. So exploring using this for a more limited type of knowledge base with less data would be interesting to see if we still are able to get good performance. Or maybe even the gap would be bigger. And of course, it's research, so there's always something more to work on. But nonetheless, the data set and the official paper accompanying this research are due to be released soon. So stay tuned for those. And I'm happy to take any questions.
We have one online question, which I will read to you. From Manoush, what if the entities to be recognized and disambiguated are very specific product names, and you just have a list of those entities and not in context?
So I'm not entirely sure I understand the question.
That's what I have.
Okay.
You know, product names would be in a lexicon or something like that normally, but maybe not inferable the way that you were describing.
Right. So you definitely have instances where you know, you have entities which don't have full knowledge base entries accompanying them, and you know, that could be product names or it could be, you know, a variety of other entity types. And so that's why for like a real world named entity recognition and linking system, like the one that we have, we don't just rely on these statistical engines. We also rely on, like for example, you can have a lexicon or a gazetteer that you use in order to enhance the extraction capabilities of your system to deal with these, I guess, context-free entity types.
Before I read the next question, I'm always glad to hear people who are not using pure straight machine learning based models, but are using systems that are hybrids of engineered artifacts like lexicons or gazetteers, or for that matter, rule sets or taxonomies. We have a question from Adil. Could you have incorporated a hybrid in-between method like persisted knowledge graph as an extension to the ADIPET model to improve on reasoning and transfer learning?
I'm not familiar with that specific approach, but we definitely could explore a number of different ways to improve the transfer learning of the system as a whole. Now, for the pattern exploitation technique itself, that is something that's more strictly, I guess, text-based. You're not really doing, you're not dealing with the disambiguation task quite as directly when you're fine tuning for that. But definitely those other transfer learning techniques we could explore.
What is the metaphor when the domain gap in the domain is so much, for example, I think maybe between the COVID and mental health, so much further between them and the mental text, but then to something like extract or regulation transcripts, that would be a higher domain gap in that text and also the topic. So does it perform worse than the domain gap and so on?
Okay, so the question is that when we were looking at a model that was trained on general news and being evaluated on mental health news, which is still kind of similar in a way, but how does the performance differ when you go from general news, for example, to something completely different, like a medical transcript? Is that okay? And so, yes, exactly. The system performance would become much, much worse in that case because the statistics would be entirely different because the nature of the text that you're dealing with becomes entirely different. And so it's specifically for reasons like that that we're interested in exploring these types of techniques, because what we would like to do is be able to handle those types of domains with relatively little data. Slide 21. This one? Oh.
So it's one that you're creating like these two recommendations that you want to are these automatically populated or are they given to you, or like how do you create all this like?
So so you're talking about where does this list come from? The list.
Yeah, how do you populate them? Are they populated by your system or are they given?
So in this research project, they're given. As I mentioned toward the beginning of the presentation, there's two subtasks of named entity linking. There's candidate generation and there's disambiguation. So the disambiguation task assumes that you've already produced this list of candidate entities and you're just trying to pick which one is right. But for candidate generation, that's going to be the process that actually takes that raw string up at the top and gives you those lists.
Let's go for two more questions that came in online. We have Manoush again. Could you elaborate on how you design the prompts that are used as inputs to the language model for zero-shot named entity recognition?
Sure. So the prompt design is admittedly a manual process. We tried a few different prompts, and in fact, for the research paper that we hope to release soon, goes into more detail about that process. But basically, our approach was we just came up with a few different prompts and we tried them on different data set sizes and just observed which of them performed the best. Now, there are other techniques we could try. For example, there's a technique called prompt tuning, where instead of handwriting a prompt yourself, you essentially learn a sequence of new tokens that you add to your language model, and it automatically learns like the best prompt, so to speak, that would capture your task. So there's definitely prompt design is definitely, I would say it's still an open problem, but there are plenty of techniques to try out there.
Just to remind any online attendees that if you'd like to attempt to ask your question live, you can use the Zoom raise hand feature, and we will enable you to ask them live, and otherwise use the Q&A feature. We have an anonymous attendee who asks, can you elaborate the business use case for DCA versus DCA adapt?
Sure. So a system like DCA does a great job at named entity disambiguation, especially if the data that you as an end user are interested in is general news style text. So in that instance, you wouldn't need this system. But if you're a customer who has data that's really from any other domain, then you need something that's able to more readily adapt to those domains. And so our hope is that with this system, what you would have is something where you can kind of broaden the scope of the pre-trained system on its own in a zero-shot sense, but also if that performance still wasn't up to snuff, you could then take a smaller amount of training data and transfer that knowledge in the system over to that domain, if that makes sense. Really, it's domain transfer is the problem that we're trying to solve here with as little data as possible.
Realize realized as I was reading that it was a DCA plus Adapet. I think that was a spelling correction when the person typed this in. That's the last question I have online. Do we have any other questions from people who are in the live audience here in downtown Somerville, Massachusetts? Is there suburban Somerville, Massachusetts? Anyway, any other last chance for questions for anyone who is online? Great. Well, so I guess that wraps it up. Thank you very much for your talk, Philip. So I'm going to stop the share and just remind everyone that we will post video of the presentation after Zoom is done processing it, and then I have time to upload it to YouTube, to the NLP XING YouTube channel. I won't bring that slide back up, but that you can find it bit.ly/NLP capitalized XING. And if you would like to give a talk at a future meetup, whether in person or online, you should drop me a note rather than bringing up the slide again. I'm at Grimes, Grimes at altaplana.com, ALTAPLANA.com, or you can message me through the meetup platform. So thanks for everyone who is attending online, and we'll have another program before too long, I hope. And thanks to everyone who's here in person. And I'm guessing the benefits of being in person, that there's still some pizza left, maybe not quite so warm anymore, but I hope you'll all hang out. So I'm going to terminate the Zoom, and thank you once again to our speakers, Marcelo Bursztein from Novacine, and Philip Blair from Basis Technology. And I forgot a question. Someone asked about opportunities with Basis, so I'm going to turn that over to one of you two gentlemen, I think. Someone asked, I'm sorry, I forgot about this. Any future NLT related job opportunities available in Basis Technology? If yes, where to reach out? I don't know who put this in, it was anonymous, but this is your chance.
All right. Normal plug, yes, Basis Technology is. Thank you. My name is Chris Mack. I work at Basis Technology on one of our development teams called the Growth Lab, and we are hiring. We've got open positions posted online, and we'd love to hear from you. So, yeah, thank you. Thanks for the anonymous post. basistech.com, BASISTECH.com, careers. Thank you, Dan.
Okay, I assure you that was a genuine question that came in via the Q&A. So we will terminate now. Thank you all for attending.